takes a while to digest this plot. I don't expect that you grasp it, but the take-home message in the end is only in 3 dimensions you should have a metal insulator transition, while in 1 and 2 dimensions electrons always become localized even for arbitrarily weak disorder. This is the statement of this theory, and actually this made quite some impact. It really produced the kind what you would call dogma in psychology. So let me now talk about the weak localization. So the weak localization is what happens here on the nearly metallic side. Let me put it this way. There it is possible actually to calculate how the resistance should behave. And the important point is that, say, this quantum conduction, this localization is expected only if the localization length is smaller than the length over which the electrons can propagate phase coherently. If they suffer an inelastic collision so that the phase coherence is lost, then you expect a breakdown. So that means for 2-dimensional really large films, you should replace the sample size by this phase coherence length, which depends on temperature, because it depends on these inelastic scattering processes, which are all temperature dependent. And because this is, say, if you approach here really 0, this is an arbitrarily weak effect. It is called weak localization, and it is accessible within perturbation theory. And there is, in the same year, actually, say, a number of very seminal works, which eventually came to the result that the change in resistance divided by the peak resistance is just minus the change in conductance, is some logarithm in 2 dimensions times the quantum of conductance. And if the resistance here becomes large and you multiply it to the other side, then you see that the change in resistance can become large. For that, the resistance has to be comparable here to the inverse quantum. And this is one of the first experimental results. So this is on copper films. The sheet resistance here is about 6 ohm. This is a good metal. And when you look at the temperature dependence of the resistance, so you see coming from high temperature, the resistance drops. This is the freezing of phonons. And then it turns around at some point and it increases again, logarithmically, exactly as this formula here predicts. So this is weak localization. And the name is properly chosen because if you look here at the scale, you see that the values change in the 4th and 5th digit. So it's some sports to measure this. And nevertheless, the scaling community, scaling theory has convinced the community that eventually this should become an insulator. Spoiler, it's not the case. So in order to see the predicted crossover to insulating systems for good metals, so KFL, Fermi momentum Fermi wave vector times elastic mean free path, much larger one. So here we have 5,000. One would have to measure the conductance as exponentially low temperatures. And if you put the number in here, you find exponential to the power of minus 15,000. My 1980s HP calculator cannot cope with such small numbers. And this actually is now advocated by Aaron Kapitulnik, who made a living for 30 years of scaling everything and everything. If you could not follow, so this is a distinguished library, which was really kind of a Bible of people working in localization. In that. Do you have questions? Yes.
So the main statement is that weak localization predicts an MIT in good metals for arbitrary low disorder at very low temperatures in 3 dimensions.
Yeah. well, not weak localization, that is true, but if you go to low enough temperature, no, in dimensions, you should, it depends here, so this depends on concentration, for instance, right? Mm-hmm. So this is the experiment that I have shown here.
Yes, I understand, yes.
Yes. But say insulation is understood as well as metallicity only in the limit of zero temperature. Only there you can distinguish. And but there was a habit to call everything where the resistance increases an insulator because eventually it should be insulated. Maybe at 10 to the minus 10,000. Okay. Oh, was this an answer?
I think so.
Yeah, so only in 3 dimensions you should find this transition. In 2 dimensions you should have no methods. And of course this is a provocation to the experimentalist who has experience with evaporating thin metal films. And say it turned out that this is actually quite difficult to make films with a high enough resistivity. So people said, okay, let's take a normal metal, bismuth, at least at usual temperatures, and let's evaporate it at a substrate which is kept at helium temperature. And it turns out that this metal is a beautiful superconductor, if it is thick enough. So the point is that if you do this with a gold film, then it breaks up into small islands of gold, and it's not a connected film anymore. It's difficult to make homogeneous and strongly disordered films. And this measurement here on ultra-thin bismuth film, you see it goes here from 4 angstrom, 4 angstrom thickness. That shows already the phenomenon which is the topic, the superconductor insulator transition. So it goes from something that is very clearly insulating to something where the resistance is flat, and then here to a beautiful superconductor. And nearly simultaneously, indium oxide is another material which can be made amorphous, and therefore also does not produce grains and blobs and so on. And in zero field, this is a beautiful superconductor. And if you increase the magnetic field, then you see that you produce an insulating state. So this is the famous magnetic field tuned superconductor insulator transition, which is still plaguing us today. So that was about localization. Now, superconductivity, I assume that many of you are familiar with the basic facts. So in metals, the repulsive part of the electron-electron interaction is strongly screened by the ion background, which is positive. And that's why arbitrary small interactions can lead to a Cooper instability, meaning that electrons condense pairwise into a new ground state, which we call the superfluid condensate, which has all these interesting properties of zero resistance, Meissner effect, and so on. And the excitation of quasi-particles displays an energy gap. Nevertheless, disorder in the shape of the normal state resistance plays a role, as say the supercurrents that can flow are proportional to 1 over Rn, meaning they become smaller, and I will precise what I mean. Moreover, the very same P.W. Anderson issued another theorem, namely non-magnetic impurities should not affect Cooper pairing. And as for many theorems in physics, they are usually valid only in limited ranges. So if the disorder is strong enough, then your electron diffusion becomes very slow. And that means now the screening is not as effective anymore. And therefore you get a competition between the repulsive and the attractive part. And that weakens the Cooper pairing. So that's an important effect of electron-electron interactions. Now, what I meant by supercurrents proportional to 1 over Rn. So we can ask ourselves, so what drives actually a supercurrent? We know that normal currents, they are driven by electric potential gradients. But in superconductors, usually we say this potential gradient is 0, at least in the stationary state. So we can ask what actually drives the supercurrent. And The answer was given by Ginzburg and Landau. The supercurrent density is proportional to the gradient of the phase of the macroscopic wave function. And because we need Gaussian variance, we have to add the vector potential here. And the prefactor in front in Ginzburg-Landau language is the modulus of the order parameter psi, which you have heard about already earlier on this workshop. So this relation I like to call the current phase relation because it relates current density and phase gradient. Historically, this is the second Ginzburg-Landau equation, but it's also very similar to the first Josephson equation, meaning, say, the Josephson equations are some discrete version of the superconductors, where you don't ask how the phase locally changes, but you have only input and output and look at the phase difference. Like in a resistor, you ask in electronics, you don't ask what is the electric potential inside the resistor, you only ask what is the voltage at the two terminals. But what happens now if we violently impose now an electric potential difference? And the answer is then our phase requires time dependence, which is proportional to the local electric potential. And that means if you have an electric potential difference, you have a phase difference between 2 points in space, which increases in time. And that means your supercurrent is accelerating. Okay, now from this equation, one can now draw two important conclusions. One, we obtain if we take the curl of this current phase relation. Then we have here a rod-grad, which is for well-behaved phase pattern 0. And so we have that the curl of the supercurrent density is proportional to some factor times minus the magnetic field. This is the second London equation, which produces Meissner effect. Now, this parameter lambda here is called the London parameter, and it has many other names. Some people call it superfluid density because they interpret here the psi squared as the density of Cooper pairs. Then you see it is the inverse square of the penetration depth. People from solid state spectroscopy, which measure AC conductivity over wide frequency ranges, they call it the superfluid weight. And I prefer to call it the superfluid phase stiffness for reasons that become obvious later. And this phase stiffness is an energy scale that just converts a flux into an energy. Finally, one possibility to measure now this parameter lambda, which tells us how strong our supercurrents are, is by the so-called two-coil technique, where you have a drive coil, then you put your superconducting film on top, and you have a detector coil on top of the film, and you measure the mutual inductance between the two coils. So if the film is normal and not too well conducting, there is the detector coil measures the full flux that is emanating from the drive coil. But if the film becomes superconducting, the Meissner effect reduces the mutual inductance. And by some fancy methods of mathematical physics, it's possible to convert this into this stiffness. And this is a popular method of measuring magnetic penetration length in ultra-thin films, which are much thinner than the penetration depth, right? So you cannot put the magnetic field in plane. There is no field expulsion, no Meissner effect. You have to put it out of plane, and then there is a reduced Meissner effect with a very large penetration. So, but now we can also take the time derivative of this current phase relation. So we have here the gradient of the time dependence of the phase, and here this the ADT, this is the electric field. And this is called the first London equation. You read about the first London equation every book on superconductivity on page 2, and then in most books it's not mentioned again, which is kind of a pity because for 30 years I was looking down on this equation. And I overlooked that this actually does something very nice. So first it says the superconductor is an ideal conductor, but no Meissner effect. On the other hand, if you put this here into units of current and electric field into units of voltage, then you see this is an induction law, and the prefactor here must be an inductance. And inductance is much, much easier to measure than actually, say, the Meissner effect in the thin film. Lucky us, if the thickness of the film is much smaller than the penetration depth, then actually the geometric inductance is negligible, and we measure only the so-called kinetic inductance, which tells us how many superelectrons are there. So that is a very convenient method to learn something about the superfluid condensate. Okay, so some few remarks why superfluid density is a term which is very visual, but maybe also sometimes misleading. So we then suggest that link the electron density to the density of Cooper pairs NS by just a factor 2, and that all electrons pair. This is wrong because this is supposed to be a delta. Only within the energy gap around the surface, semi-surface, electrons pair, not everywhere. And it is an artifact of the free electron model that it works in this case, that you really get half of the full electron density in the clean limit. However, if you have this order, this prefactor, lambda L to the power minus 1, strongly depends on the mean free path, while the density of Cooper pairs should not depend on the mean free path according to Anderson theorem. The Cooper pairs still propagate dissipationless, but still they need to diffuse, and this diffusion is slow if the disorder is high. Therefore, the supercurrent carrying capacity goes down if we increase the level of disorder. It has nothing to do with density. So this is something that Andrei also pointed out, that at least within Ginzburg-Landau theory, only the ratio of ms to m star is relevant, because, and that is actually 1 over the lambda squared. And one can actually decompose the supercurrent into a supercurrent density and a supercurrent velocity, but we should not think that these are fundamental concepts. In the end, it is just one parameter, which is a kind of response function in the sense of linear response theory that tells us how strong the supercurrent is. And microscopic theory also gives us a value, what this lambda is supposed to be. And you see here is the 1 over n. So delta divided by Rn, the normal state resistance, tells us how effective our superflow is for a given phase gradient. And you see that this expression is clearly different from Bude. Okay, so that was a tutorial on superconductivity. Any questions to that? Yes?
Is the thickness of your film lower than the penetration depth? Does this method work?
Yes. Then it becomes nice. Because only when the thickness of the film is smaller than the penetration depth, then we have the kinetic inductance dominating over the geometric depth. So this follows here from this formula. So the first part is the geometric inductance, and the second part, so here this is L kin to the power minus 1, the inverse. The d is here in the denominator. What's called up it is, while lambda is in the numerator or denominator, the bottom part. So that is why if lambda is much larger than the thickness, this term wins over the first one, over the geometric inductance. And that is for the strongly disordered superconductors, this works very well. Okay, more questions? Yes?
How in practice do you discriminate this effect for phase thickness between the disorder and carrier density?
Oh,
how do you know what is a real like contributor?
Well, what do you mean real contributor? So in the end, we have here a formula where the Rn, if you wish, contains both the density and the mean free path. It's in one parameter. And the delta, the strength of the pairing, is of course also important.
Okay. Okay.
Yeah.
That's a very naive question, just to continue on that question. And it's an atomically thin sheet.
Yes.
Is D zero the Bohr radius, or is it replaced by some other physical length? What's the thickness of an atom?
That is the beauty of the sheet resistance, that you don't care about thickness. So it's of course one atomic layer, and there are experiments like this. So our friends from surface science can deposit lead on silicon surfaces, and they find that there are monoatomic layers of lead become superconducting, and they can be measured with this method, with the Foucault method. Has been done. There is no problem.
But in the formulas, then what's the D you put?
Well, you see here in this formula is no D. There is only the lambda. That is the quantity you measure. It is also always small lambda. Here is a D missing in the it's not one. It should be D. Where do I have it?
If we were to assign a D, it would be the Bohr radius.
Yeah. Well, not maybe the radius, but twice the Bohr radius, or the radius of the atom. Lead atom, which is not exactly the Bohr radius probably, but something small. But interestingly, these lead films, they're relatively highly ordered. They have a sheet resistance of 60 ohm. So this is only 10 times more than the stupid copper film. So atoms conduct really very well if they are in the metallic crystal. One layer, also for the TMDCs, and so these mono layers, they have a relatively small sheet resistance of some 10 ohms. This is important because, for instance, you can never observe Kosterlitz-Thouless physics if the sheet resistance is that low. Okay, now I come to this topic: suppression of zero resistance state by phase fluctuations. And that is the celebrated Berezinski-Kosterlitz-Thouless transition, which was invented some 50 years ago, and as usual, with appropriate delay, some Nobel Prize may be awarded or not. So there is actually an energy cost for distorting the phase, right? To produce phase gradients costs energy, and the superfluid stiffness, proportional to the superfluid density, tells us how big is this energy cost if we have here such a gradient of the factor if you view the superconductor as an orbital parameter field. So this is the ground state, meaning that there are no phase gradients within the superconductor. All so the arrows here they are, say, a local phase angle e to the I phi. Phi is an angle. If it's constant, then there is no such energy cost. And what can now happen is that defects are occurring, which are of such circular natures. So if you translate this into a current flow pattern, then you find this is a vortex and an anti-vortex. And we are used to think in vortices in something that is generated by magnetic field. But here it is not the case. So such perturbances can be excited simply by thermal activation if the superfluid stiffness is small enough. So if the superfluid stiffness is comparable to the transition temperature, then it is possible to thermally excite vortex-anti-vortex pairs. It have to be pairs, because otherwise you would violate angular momentum conservation. And actually say these vortex-anti-vortex pairs with opposite current orientation have the property of attracting each other. like even orientated vortices that you have in your apricot of lattice, they repel each other. Okay, and if they attract each other, means you don't see these vortices necessarily in resistance as long as the current is small enough not to rip these vortex-antivortex apart. So there is a net Lorentz force acting by the DC transport current on these pairs, and there is no dissipation. So if your superconducting film has low enough superfluid stiffness, then you can excite those objects, but you will not see them. You see them only if you rip them apart and they can move individually. And that is the destruction of the zero resistance state by phase differentiation. So I will elaborate on that. So basically, you have a situation where you have this catamaran here, which is vortex and anti-vortex, and there is a bridge in between. But if you apply enough force, Lorentz force, on this pair, then you will separate them. Or if you go to higher temperature, you can break this bond. And then the vortices are unbinding, and you see them in resistance. So the signatures that have been predicted long time ago was that the superfluid stiffness should depend on temperature, because superfluid density, if you wish, depends on temperature. But, or delta depends on temperature is the better statement. And then there should be a sudden drop. And this physics has been first observed so cleanly observed in liquid helium films, which are another manifestation of, say, superflow, not charged. So this experiment here is done with a torsional oscillator, which tells you how much of the superfluid follows the motion of the torsional oscillator. And these are thin helium films, and they become thinner and thinner, and the thinner they become, the lower is actually the superfluid stiffness. And this black line here, that is the big prediction of this Costa-Desardes theory, that there is a universal behavior in the sense that the jump of the superfluid stiffness or the Costa-Desardes position occurs precisely always at this value. And you see these helium films obey that. And yes?
If you put a low enough current, then you don't break this vortex-antivortex pair, but and you oscillate this current so that they do something like that. Should you see it in resistance?
Yes, I come to that. So we measure this, and indeed we measure this with an AC method. And what we see is that the damping, and use a resonator method to do this, and the damping actually already increases. The Q factor goes down 1 Kelvin before the transition temperature. So there, I think we see it. Although we have not analyzed that quantity. I think that's. So we have a kind of cartoon for the Costa-Desardes physics. So there is, say, in black, there is a DCS. Temperature dependence of the stiffness, and in the vicinity of this crossing point, the thing should jump. So that this is crossing here is not at zero. This is renormalization physics, which we ignore for a moment. And so these are important experimental realization based on this two-coil method that I have explained to you. So this here is a really pioneering experiment. You see 83. This is an indium oxide film again. You see the stiffness here is half a Kelvin. Tc is 1.6 Kelvin. This is the condition you need, right? You need enough disorder so that your stiffness goes down. And then you see with the isobar, yes, indeed, so there is some decay. This here is a much more recent experiment in niobium nitride. The material is also studied in my group. And you see in this blue dashed dotted line is what theory tells. So here should this universal jump occur. Red is the BCS, mean field behavior. And you see the data here are this black line, where you see the transition is really broad. It's not the sharp jump that is predicted. And also here the jump is not so terribly small. And so always when you see a smear transition, then say theoreticians are quick in saying these are finite side effects, even if they have nothing to do with the size. And it's actually due to Laura Benzato, which I missed to cite here. But she has clarified that this cannot be the case, but that this spreading here must come from material inhomogeneity. And we could actually confirm that this is really the case. It is material inhomogeneity, which is particularly sensitive for this two-coil method, because you need, say, a 10 millimeter diameter disk, to do the two-coil method. And the edge of the disk, your superconductor is always a bit worse, right? So 5% change of stiffness at the edge are enough to produce such broadenings. That's what happens. Yes, please?
As I recall, in the helium-4 films experiment, the broadening was coming from the finite frequency of the measurement. Yes. That is not an issue here at all.
The finite frequency effect that has been actually demonstrated here by these authors produces basically a shift and not so much a broadening. At some point it also produces, but this broadening does not change in the frequencies here. This was, I think, from 10 hertz to 10 kilohertz or so. Yeah, it has an effect, but it's relatively small. Okay, so how can we do this practically? So we didn't do the two-coil method. We tried the two-coil method. We found all these broadenings as everybody else. But then at some point I understood that this first London equation is not as stupid as it looks. And it can be used to actually say put a superconducting film here as an inductor. And if it is resistive, of course, there is a series resistor into a resonance circuit. And from the resonance frequency, we get very nice quantitative information about our stiffness. And we work, as you see here, at a frequency of a few megahertz, also to keep this finite frequency effects within bounds. And yeah, it worked. So these are your different temperatures that you see here. It noticeably shifts the resonance. And you see, even if the resonance is very broad, quantity factor close to 1, the superconducting qubit people will look down on me, but we work with Q factor 1, and it's still enough to extract the stiffness by 3 digits. It's not a bad method. Okay, so this is how it really looks in our case. So green is the superconductor, blue is edged away, and you see we have here a nice meander. In order to have enough squares in series, 100 squares to be precise. So this gives us a nice inductive signal, and this gives us also a nice resistive signal. And both can be measured on the very same film in the same cooldown. That is a nice thing, as a big advantage as compared to the two-coil method, where you cannot measure resistance on the same device. So we have 3 nanometer thin niobium nitride films on which are prepared by atomic layer deposition at Jena. They do this for 15 years and have really perfectioned that. We pattern these meanders, and we have, say, sheet resistances at room temperature of the order of a few kilo ohm. And you see here the size is 200 micron. Our device is much more compact, and that's why we are not prone to this material inhomogeneity. Now, if we first measure resistance on this device, so you find here a superconductor transition. My supervisor at PhD times would not have liked it. Said, what bad sample have you made that the transition is so broad? Because, say, from the bulk community, broad transitions always mean sample inhomogeneity. You have made a bad sample. But here, in this case, you see we have theory curves that describe the top of the transition and other theory curves which describe the bottom of the transition. That's precisely what Andrei has explained us the day before yesterday. This is the famous fluctuation superconductivity, which is a quantitative theory. And this theory, the red curve, allows us to predict what the mean field transition temperature is supposed to be. The temperatures where Cooper pairs form. This is not the temperature where the resistance is 0, obviously. because this blue curve here, this tells you how vortex, anti-vortex pairs unbind. And we can put this rather on a linear scale, then you don't see much of this, but if you put it on the logarithmic scale, then you see that there is now really, say, a sharp transition, which is this Kosterlitz-Thouless transition. And the blue line is a very famous formula, the so-called square root cusp formula, because you have an exponential, and then in the exponential you have something that diverges. So that really produces a sharp transition, and that is the Kosterlitz-Thouless transition. So we can actually play on and go to nonlinear transport. This is another seminal prediction of this theory here. You see it's also from 80s, from 78, 80, and so it's all 45 years ago. And they made the statement that current voltage characteristics should have a power law character, and the exponent alpha here is universally related to the superfluid stiffness. In principle, IV characteristics would be a method to also extract the superfluid stiffness, if there were not a slight caveat. So this is again the Fiori experiment, which is really groundbreaking, because it has used a split picovoltmeter. You see, they plot here V over I. I is microamps, and resistance here is say 10 to the minus 6, 10 to the minus 3. It's micro-ohms, and that leads really to a picovolt resolution. And here you very beautifully find power laws, which can quantitatively relate it to the superfluid stiffness that they have measured independently with this two-pole method. And this is another example here from Tatiana Baturina on titanium nitride balloons with a conventional voltmeter. So here this is 10 nanovolt, the scale. And also there, you see ohmic behavior, smaller and smaller resistances, and at some point the slope changes. And here is this magic exponent 3, where the Kosterlitz-Thouless transition is supposed to take place. You find many examples in literature, also very famous seminal papers, which I do not criticize for the breakthrough they have achieved, but which actually analyze IV characteristics somewhere up here. You see also here the slope changes, and of course you will find an exponent 3 here somewhere. But this exponent 3 has nothing to do with Kosterlitz-Thouless physics, it's just electron. This one really has to know, this is the ohmic straight line from the normal state. You have to go several orders in voltage below to be able to detect this Kosterlitz-Thouless nonlinearity. Experimentally, it's a difficult thing. And I had a very talented student, Alex Weitzer, see here's the shift, who also did this kind of stuff. So there is, here is the ohmic straight line, you see here at 10, and then 3, 4 orders magnitude lower. There is still some linear behavior, which comes from the linear resistance somewhere here in this part. And this linear resistance really becomes very small, okay? So, if one is careful enough, and of course there's always a detection limit, then indeed one can see, okay, here is slope 1, heating is somewhere way up, and then this slope changes to the magic exponent 3. Now you cannot read this, but this is embarrassingly close. From the resistance we find 4.571, and here we find 4.475, 4 millikelvin difference, which is of course an accident, but I would say within 20 millikelvin we get regularly the same result. This is already quite encouraging. And now we can complement this with our inductance measurements, and it's again compatible within 20 millikelvin. Totally different result method. Here now we have a sharp jump, a really sharp jump, because we don't have experience in homogeneity. And the red and the blue arrow, they tell you where from resistance data you would expect the pairing temperature, the mean field transition temperature, and the Kosterlitz-Thouless temperature, and agrees very nicely. So I would say we really understand the Kosterlitz-Thouless transition in this material. Yes?
in the experiment, what is the magnetic screening length compared to the size of the sample?
The magnetic screening length is a so-called Pearl penetration depth. That is 2 lambda squared, the usual penetration depth over thickness. That's millimeters. It's far larger.
Okay, so you are in a regime where your superconductor is more or less like a superfluid, in the sense that there is no Meissner effect inside the sample.
Yes, there is the Meissner effect is totally negligible. Field penetrates homogeneously, except for these thermally excited vortex-anti-vortex pairs, which has nothing to do with the external field. Well, I should say magnetic field in this experiment is bad because it disturbs the balance between vortices and anti-vortices. If you have an external field, then of course you have more vortices than anti-vortices, and then you always see a resistance. So you have to compensate the perpendicular component of the magnetic field, perpendicular to the film. You have to compensate that down to 1 microtesla. And that's what we learned, how to do this. In the old times, people had a double new metal shield, and Fiore even then an aluminum shield around the stuff. But it works also if you carefully compensate. But you cannot just work with the given Earth magnetic field. That is too large. You have really to avoid that. And you can also, this experiment has been done in a big superconducting magnet, 12 Tesla. Well, if you have been at 12 Tesla before, first you have a rest field. This you can compensate, but then this rest field has the property that it jumps over time because flux is released over days. So if you then do these experiments, the pure student becomes crazy because the compensation is spoiled every half hour. You really have to warm up your magnet above its critical temperature, 40 Kelvin or whatever, and to get rid of all this trapped flux in the magnet, and then you use a tiny power supply and put some microamps of current through the cables where you usually have 100 amps. Okay. Now we can compare the slopes that we actually extract from our V characteristics using this formula, and it really falls very nicely on the stuff. And I'm proud of this graph actually. One more caveat about current voltage characteristics. So you see, these are our current voltage characteristics. And if you want to put 10 volts to a superconductor, you have to use these nice meanders. And down to microvolts. So this is really some 8-9 orders of magnitude in voltage. And the beautiful data that you see here, which produce this very nice agreement, they are extracted where you have this gray rectangle. If you go a little higher, then you see first electron heating, and here you even see heating of the stage by sending the current through. That's why this nonlinearity of IV characteristic is a popular method for the Kosterlitz-Saulus physics, but it's a very dangerous and delicate one. I don't recommend. So now I have half of the talk, and how much time did I use?
Half. 55 minutes.
Please keep questions, except you want to have an early lunch.
Do you have any idea how solder affects this Kosterlitz-Saulus transition? I mean, destroys superconductivity?
Yes. This will be the subject of my talk next week. And the answer is we can follow the Kosterlitz-Saulus transition all the way to the superconducting insulator transition. And it remains a beautiful Kosterlitz-Saulus transition.
Same as in the IP.
We have measured only sporadically IV for the problems that you have here. But let's say the comparison between the linear resistance and the superfluid stiffness works out very nicely. This is a talk on its own. That's why I did not include it in there, but it's interesting. It's
yeah, next week.
Yeah.
Maybe could you summarize or tell us what about the actual superconductor BKT transition? So if the Pearl length was much smaller, Then there are fluctuations of the electromagnetic field that need to be taken into account. So there are these various theoretical predictions. It's a first order transition or not. Is this something that people measure?
I didn't catch the question so far. The Pearl length is much larger than our sample.
Yes, so it's effectively a superfluid. You have a decoupling.
And I thought, what could I have else than a superfluid?
Yeah, but perhaps you could experimentally have somehow a sample that you're measuring that's even bigger than this lambda, so that lambda pearl is not effectively infinite, but it's somehow finite for you. It's not the biggest length.
Yeah, so we see finite size effects in these devices, which are on our poster outside. It turns out that lambda is totally irrelevant. I mean, the lambda pearl is really irrelevant because there is always a finite size effect, but it can be at arbitrarily small voltage. So if you really say the depth of the attraction potential between vortex and anti-vortex in this film is some 1500 Kelvin. It is a super deep thing. And if you now cut off the logarithmic interaction by finite size, you can go down to 200 Kelvin and still measure reasonable. So within the 5 Kelvin we are operating here, you see beautiful Costa-Lestaulis physics. All finite size effects are happening at atto-volts, which we don't measure. Yes?
Continuing on the next question. But imagine, even if it's not doable, that you could just have a node for the pearl length.
Yeah.
You could make it now very, very small so that your Meissner effect is very strong, even though you're still in the 2D system. And then the expectation is that the vortices, they no longer interact, and therefore the Costa-Lestaulis transition temperature, it's pushed down to 0 temperature. That's the expectation.
Yeah, if you make the pearl length small, then you can do this in 2 ways. You make lambda small, but then you increase your stiffness far above the mean field temperature, and then you don't see Costa-Lestaulis physics, or you see it only microkelvins away from your mean field transition. Then you cannot observe that. The other way is to make the thickness small. Here we have only a factor 10 to go, because then we are at 1 lattice constant. And I think this is not a realistic situation.
You would rather make the thickness larger.
If you make the thickness larger, then, so we have now here a Costa-Lestaulis temperature of 5 Kelvin. If you make 10 times bigger thickness, we have 50 Kelvin, and also bring the Costa-Lestaulis TC to the mean field temperature where we cannot resolve it anymore. So the point here was that you have this 10% distance here between Costa-Lestaulis and mean field is only because the stiffness you see here is 7 Kelvin. If you go here, in fact, I should bring a slide maybe next time. If you crank it up by a factor 10 of 100, then actually your universal line is somewhere here, you see, and only in that area you can see Costa-Lestaulis. And that's not feasible, I think.
Will you say hysteresis in the current voltage plot?
Well, if there is enough power, yeah, you see here there is a backbending. So this is because we have a series resistance. If you do this without series resistance and pure current bias, you will jump up here.
Okay, so here these plots are in the direction of current increasing or current decreasing?
These are in the direction of current increasing. But it doesn't matter in this regime where you can extract the physical interesting exponent. Yeah.
What happens if you play with disorder? If you make cleaner, slightly cleaner, or so?
Oh yeah, that's
play with
if you decrease the disorder, then you walk with the Costa-Lestaulis transition towards the mean field TC. You increase disorder. In our most extreme example, the stiffness goes like this. Yeah, we managed 200 millikelvin, not 0 yet.
I have have another question with the ID curves. So if I understand correctly, the first slope is really, let's say, what's not affected by electron heating, and then the upturn that you see afterwards.
I mean, there are two effects that do that. Electron heating is somewhere up here. The first effect that you see here is current-induced impairment. Because this, if the stiffness is still very small, the action between the vortices is small, and if you put up your DC current, you easily pull them apart. That's why you have power law behavior also here above Kosterlitz Staules. Because most of here in this regime, most of the vortices are still bound, and only a tiny fraction produces a tiny resistance. And if you have your brutal DC current, then you just increase the number of vortices, and then you get a nonlinear behavior.
That's why you don't see this change of slope in the higher current curves, because then you sort of separate directly the vortices.
Are there any prospects of imaging vortices and anti-vortices in this region?
Yeah, this is a very beautiful question. This is bad news for the people that measure magnetization, like Bina, because your vortex is millimeters big and overlaps with all the other vortices. With the SDM, you could go and see whether you find a tiny 5 nanometer vortex pore. Coherent length is small, but you have to see temperature is large enough to create vortex-anti-vortex pairs. That means this is a dynamical equilibrium. They appear, they disappear. It's something like, can you follow a single electron in a semiconductor while all the time it recombines and you're excited? I think this is, I would not give my student the task to do that. So that was a question.
So for this data, so how can we define the critical current? What is your recommendation?
I think, so you have to ask yourself, there are several critical currents. Insulator has the deep herring critical current, which is usually very difficult to measure because there are many smaller critical currents. In particular, say, if you talk in terms of standard superconductors, there is, you measure this in magnetic field, and then there is a depending critical current. Here is no magnetic field, but if you drive a big current through the film, it has its own field and will create vortex-anti-vortex pairs, or will create vortices by the current itself. I think I can tell you the magnetoresistance of these films, upper critical field is 10 Tesla. The magnetoresistance is beautifully linear all the way up to 10 Tesla. It's pure flux flow resistance. There is no critical current. I mean, this is maybe too strong. In principle, there is, of course, but I think it's difficult to access.
So so just for clarification, the vortex, the length of the vortex is given by the parallel length here.
The extension, yes.
The extension, yes.
That's much larger than our sample size. But of course, there's also not too much current flowing outside. You see, the bulk of the current flow is in the vicinity of the core, and then it decays, of course, as 1 over r. So at millimeters, there is not much left.
Your R versus T is quite smooth and going down all the way.
Yes.
When you see a sort of a bump before the tree, there are some R versus T where you see an increase and then a decrease.
Yeah, also here there's a maximum at 20 Kelvin. Yes.
But you don't, because you're not resistive enough, not disorder enough?
Yeah. If you increase this order, say here you see this goes up to 20 Kelvin. On the logarithmic scale, you don't see a maximum. But if you zoom in here, you find a clear maximum. And that is because you have logarithmic corrections to the resistivity from room temperature down to low temperatures, which is mainly Altshuler-Aronoff, and then the superconducting fluctuations start to bend it down. So for the higher disordered films, this becomes much more peak.
I have a question regarding the currents. Can you maybe show the log plot of the IB again? There is some in the red curves. There's some sort of kink, you said, yeah, it's due to the
Current-induced pairing.
breaking up. Yes.
Yeah.
Isn't that some sort of critical current?
I think it's really an undefined thing because it totally depends on your criteria. You say usually we are used to flux thinning, flux creep, flux flow. This is the terminology that you have in standard superconductors, and flux creep is something exponentially small.
Is this not the deep pairing current that BKT is talking about? Is this something different?
BKT does not talk about deep pairing current. This is okay. So there is deep pairing of vortex-antivortex pairs. Yes, that is what BKT is talking about. But in the usual language of superconductivity, deep pairing means deep pairing of Cooper pairs. And that's a much, much higher current.
Yeah. Thank you.
Yes?
Not related to the main part of your talk, but you mentioned Kravchenko.
Yes?
Could you say a few words about what the status of understanding that physics is?
At the end.
Okay, thank you.
I have a slide for that. Not that I can add much understanding. There is a review. Yeah. Okay. So I continue. Now, this was a long chapter because that's also a big part of our work, and I use it as a warm-up for what I want to present next week. Now, what is suppression of Cooper pairing by disorder? So we had this seminal picture here, and then now there are two effects actually on the order parameter by the disorder. One is the suppression of the amplitude of the superconducting order parameter, and the other is that if the amplitude is unaffected, but phase fluctuations destroy the stiffness. So these are two branches of superconducting insulator transition that I want to discuss now. And the fermionic approach, let me call it, that actually is precisely what I said. If the screening becomes weaker because diffusion is very slow, then the repulsive part of the Coulomb interaction, of the electron interaction, destroys both delta and TC. And this is described here in a seminal work by Finkelstein. I think this is this nonlinear sigma model, so theoreticians will not. And this is an important tool for the experimentalists. It's not so digestible. So I just gave you the result. But interesting is that now the suppression, TC0, is now the transition temperature up here. This is the ratio, and then this is a monotonic function, and it contains here parameters T and gamma, which are both related to the Drude scattering time. The gamma is exclusively Drude scattering time, and T also contains electron density. So in principle, very few fixed parameters determine this kind of fit. I should say the scattering times that one extracts from such a fit are typically shorter than the transport scattering times one would extract from density and resistivity. But in these materials, the resistance is so high that the corresponding gene-free path that you would extract from naive Drude model is subatomic. It's picometers. So I think the Drude model really cannot quantitatively apply here anymore. It's also the reason I think why quantum corrections seem to persist up to room temperature, because this logarithmic decay goes up to room temperature and even above room temperature. I think this is also from the normal state. This is not really analyzed and understood.
For a model germanium, which are the data point that are shown here,
it's not that extreme, you see,
Yeah, so if I remember correctly, the mean free path time that he extracts from that is reasonable.
Yeah, well, I was speaking about niobium nitride. That is.
Sure, but polygermanium is also amorphous, so it should be roughly the same, no?
Yeah, so I don't know why I would say the discrepancy is not disturbing to me. Yes, because I think Also, this theory, as difficult as it is only an approximation. Maybe it works for monogermanium, but I mean, I can only say you what we measure. I say there's one interesting thing, is namely what we found is that the Hall effect from which we extract the density that you need to extract the scattering time is kind of temperature dependent. I have the suspicion that there are localization effects in the Hall effect. And we cannot naively extract the density from there. So this is one possible origin of the discrepancy. And you see this goes here up to 2 kilo ohms, we go up to 20 kilo ohm in sheet resistance. And this is what I can say. And so this is, these are, say, these ALD deposited films. That is in Alexei's book. There is this term which comes from the Ginzburg-Landau level. There should already be a suppression by Gaussian fluctuation of the order parameter. And the electron-electron part is the other light blue line here. And if you multiply the two terms, then you have something that reasonably fits with it. And it turns out that this curve is also very telling in the end because it determines all other properties together with R. Okay, but this I will next week. So that is what I wanted to tell about the fermionic approach. It's not much. It's relatively short because I didn't bother you with a nonlinear sigma model otherwise. Okay. Now comes the next main part, the direct superconductor insulator transition. So these failed superconductors and insulators, these are ones where one goes through a metallic phase, which is forbidden, of course, according to the gang of four. This is the next step. Let's first discuss the direct superconductor insulator transition. And you see here again, 1990. I was still working on my PhD during that time. Immediately after these experiments on these superconducting films appeared, there was a seminal paper by Matthew Pisher, which basically said there should be a continuous quantum phase transition between a vortex glass phase, which is superconducting, and a Cooper pair glass phase, which is insulating. And this is related on scaling theory and duality arguments, which basically tell you, okay, here electrons pair up and form a condensate, and the vortices are localized by residual pinning. That's why we have and of course by the Costa-Lestrange attraction. That is why the resistance is zero. And in the Cooper pair glass, Fisher's idea was just opposite, based on duality, meaning Cooper pairs are localized and vortices are supposed to form a condensate, and this condensate produces infinite resistance. I would love to get a hand on this vortex condensate. In 40 years, I think there's not much direct evidence on it. So this is now my crash course on this scaling theory. So as in any continuous phase transition, there should be a divergent coherence length. So R is in our case the resistance, the normal state resistance, and nu is a critical exponent that controls this divergent correlation length. There can also be other parameters like thickness, magnetic field, gate voltage, and so on, which you can use to induce this superconductor insulator transition. There should be a vanishing energy scale, which is a Costa-Lestrange temperature, like Aviat said, it should go down to zero. It is controlled by another critical exponent called the dynamical critical exponent. And then it depends on the Z nu. And another popular control parameter is magnetic field, where the same should happen. And one can extract this interesting relation here between the critical field for the field-driven superconductor insulator transition and the Costa-Lestrange temperature. And most importantly, and most popular for experimentalists, the resistance is predicted to be some quantum resistance and then a universal function which has this argument where the field dependence and the temperature dependence are combined, and these critical exponents are other ones than the ones in zero field. So we have a phase diagram of temperature, magnetic field, and another control parameter, which I chose here to be the resistance.
Christoph, is scaling is it related to the bosonic approach?
I think that is the bosonic. This is precisely the bosonic approach. No,
it's true for any condition.
It's true for the fermionic also.
Not with the same exponent, but it should be the same. It's same kind of.
well, here in the Finkelstein, there is no transition. Maybe there are, say, elaborations further. Okay.
Has to be you can scale one side.
Yeah. Okay. Maybe it's even more general, the scaling theory. I understood that these vortices are. I read the Fisher paper. I read a lot of localized bosons. Mohit certainly.
I think what you're saying is correct.
Yeah.
If you look at Matthew Fisher's paper and the later works, they're basically saying that all the electrons are gapped out and the important degrees of freedom of bosons, and this is the scaling. If the electrons are gapped out, then you can take this bosonic approach, but it's not clear.
I mean, maybe it's not the only possibility. That's what you say, right? You say you could do this with fermions as well, maybe. Yeah. But it is not what the spotlight of Fisher is, as I understand. Yes?
I have a much simpler question. What exactly, you must understand what this function f is, because it can be any function, this is generally true.
I will show you. So I took an example from Claire, which is a thickness-driven transition. So the point is here that this functional form implies that there is a crossing of the resistance isotherms. So in Claire's case, here is not magnetic field, it is thickness which is standing there. And you see here is this crossing with the eyes of love. At least you see that the black triangles are here at the bottom, and there they are at the top. And the blue circles are here at the top, and they are there at the bottom. So the characteristic property of this argument is that it produces such a crossing. And the observation of such a crossing over decades was the hallmark of the superconductor insulator transition. And see, of course, in thickness you don't have so many points, but the crossing point is somewhere here. And here in this large scale it is hardly visible. And now comes the scaling function. So if you now let this Z nu product free, then you can find values, and in this case Z nu equals 0.4, where the curves for all the different temperature fall on these two branches, where this is the superconducting branch, and that is an insulating branch. So this is the answer how this function eventually looks like. Because here is the argument as a function of thickness, similar to up here. So this is one example, and there are so to be give a tribute here to Kapitulnik, who actually then say commercialized this. This is now resistant as a function of temperature for different magnetic fields. And one sees here it's a reasonable transition. Here is something that should be governed by vortex physics, essentially. But then one can draw here a horizontal line, and then there is a point, a magnetic field, where the curves start to go up. And as we have learned from the gang of four, if the resistance goes up, it must be an insulator. Even if the resistance difference between the insulator and the superconductor is only 10%. I mean, there's this strategy that if you go to zero temperature, 10 to the minus something, this should further go up, and this should eventually go to zero. This is the spirit in which these data are interpreted. And here, as you see, a very similar scaling function, but a very different critical exponent. And this I should have an index B because it is for the magnetic field. Now, indium oxide, which is another popular amorphous superconductor, also has such a crossing point, and one can also do such a scaling. But the critical resistance is here, say, around 8 kilo ohm. Here it was about 1.7 or so. And in Claire's case, it was something like 600 ohms. So these parameters vary wide. And yeah, so this can, yes?
The principle in the theory should be 6 kilo ohms. So,
well, if Mohi has a very strong opinion in this case.
It's not strong opinion. I think it's a general fact about critical phenomena that the exponent should be universal, but the location of the critical point not. Okay, having said that, let me finish. Matthew Fisher made a very clearly stated assumption that the theory is self-dual between the two Cooper pair glass and vortex glass. If it is self-dual, then the critical resistance is universal. But that's just an assumption. In general, there's no reason why the theory should be self-dual, and therefore we don't expect the critical resistance to be universal, but we would still expect if you believe in scaling, we would expect Z times nu to be universal.
So I think there is a conceptual difficulty here, namely the scaling function is such that you have crossing points of straight lines. And usually say in the theory of physical phenomena, it looks a bit different. You have a divergence, and then you have really a point where something dramatic happens. But if you have just a linear crossing, then the closer you go to the transition, the tinier your effects are. The more linear these curves become, and it means in the end, the observation of such a crossing point means simply that there is a temperature-independent region for the resistance for different values of the.
It's all based on the assumption that there are two possible crossings, either superconducting or insulating. So basically, the separatrix has to be more or less flat.
I agree.
The crossing is nothing more than that.
But if you come, say, from the phenomenological point of view, if you have a plateau in R of t, you will observe a crossing in the corresponding curves, regardless of the origin of the plateau. And that is the problem, that if you observe the crossing point, you can say, okay, there must be a flat portion, but you cannot necessarily say that there is a phase. So the questions one has here is, say, do we really call this an insulator, or is this a metal with quantum connections? In the indium oxide, the insulator here is more spectacular, so still there is something. But of course, there is not this criterion that the resistance in the limit t equals 0. It's not applicable here, right? So how universal is the scaling? So you see the exponents are widely divergent. And the question is also how significant it is, because it does not necessarily signal that there is a quantum phase transition. And just to show you a bit more, so there are examples in the literature where people find two crossing points, you see, two-stage magnetic fields, superconducting insulator transition, meaning your R of t has two plateaus. Then you can do this twice in a limited temperature interval. Then here, an example from Paris, multiple quantum criticality, also a high temperature and a low temperature with different exponents. And just to tease you a little bit, this is an experiment from my group on the titanium nitride. Here you see the crossing point is a bit blurred. And the reason is that we can actually identify 3 plateaus in the characteristics. And maybe this is a bit too much of a good thing, a bit too much quantum criticality in the single device.
I think this is related to Griffith's kinds of stuff.
I don't understand a word about Griffith. What I learned from my colleague Ferdinand Evers is what we call in this field strongly disordered superconductors with a sheet resistance of some 10 kilo ohm or so. In theory, is not strongly disordered. You can go into much more into the localized regime, and then you get Griffiths fields. If I look at the resistances here, okay, they plot only resistivity, not sheet resistance. Here is 300 ohms in this case. Here is 300 ohms. I think this is not strongly disordered. And this Griffiths papers, you may know more about this. What is the typical resistance? Few kilo ohm.
the resistance doesn't matter. It's just the crossing point keeps moving. So your data looks really like resistance.
Crossing point keeps moving means the resistance has no plateau, but just varies as it likes.
Yeah, it goes up when you lower temperature.
We can discuss about this. I have the feeling this is even worse than the situation.
Or that maybe the resistance is not a good parameter to scale.
Could be, yeah. I don't know.
But the thing that the crossing itself means plateau, and this I agree with you. But the scaling is a different story.
Well, everywhere you have a crossing, you can do the scaling. Because you always can scale straight lines.
Yeah, but depends on the temperature scale.
Yeah. So these are over certain.
If you scale it over, I mean, if you can renormalize it over 10 milli, then
well, I think here in this case it's something like 200 milli-K. And it turns out, well, at least we have a paper on this. It's quite extensive. This was the teaser. I don't want to spend my time here. The teaser was successful.
If you look at the way Matthew Fisher's theory is made, it's a theory about a quantum critical point. It's a zero temperature phase.
Yes.
And therefore, talking about a high temperature crossing, a medium temperature crossing, a low temperature crossing, makes no sense theoretically.
Matthew Fisher says here, there you should have your plateau. And you find many examples, including indium oxide, where the low puncture part is not in the data because it spoils the nice crossing.
yes, my point exactly. I mean, scaling the.
But of course, if you have a material like this one, where you have 150 millikelvin TC, or like yours, I will also show another plot of you later, 60 millikelvin TC, then there is not much room where the temperature still can vary. So you're safe.
I know, but the resistance varies. But okay.
Okay. Let's now come to what I prefer to call insulating. So this is work from Danny Shahar's group, Weizmann, and you see here what reads here like Mala and Malf is actually MA1A and MAF. These are two different devices, different in oxygen content, and one sees one really the resistance goes down by 3 orders of magnitude, and the others the resistance goes up, not 3, yeah, 3 orders of magnitude. So that's now a clear distinction between superconductor and insulator, and I feel much better. Still, there is this beautiful crossing point. But you see that the resistance can here, it's gigaohms, right? And rho means sheet resistance, rho in 2 dimensions, the sheet resistance, is 1 gigaohm roughly. And if you look at this insert, this is an Arrhenius plot, resistance as a function of inverse temperature. If that is straight, you can expect an activation energy. And this activation energy is here of the order of Kelvin, and it strongly depends on magnetic field. And this was obviously done in the high field lab in Tallahassee also, which are the people I have suppressed here in the upper list. So this is superconductivity related insulating behavior. These are insulating superconductors. And another signature that is here is in the nonlinear transport. So this is differential conductance, the IDV, as a function of DC voltage. And if one ramps the voltage up, one finds a discontinuous jump over several orders of magnitude. If one goes back down, then one approaches 0. So there is a spectacular nonlinearities in the current voltage characteristics. This is an example from our group in Regensburg, where material was brought by Tatiana Batupina, comes from also by ALD from Löwen, IMEC. Also a clear distinction between superconducting and insulating behavior. And you see what means direct superconducting insulator transition means samples that are indistinguishable at 1 Kelvin still decide whether they become insulating or superconducting if you go to lower temperatures. And again, an Arrhenius type of temperature dependence here in the insulating regime. And if you look at the magnetic resistance, you also find a strong maximum here. Interestingly, also in the interesting regime, here it also goes over a maximum. And at a few hundred millikelvin, the curves are indistinguishable. So this is really something that happens only at the very low temperatures. And we interpret this non-monotonic shape here as arrays of resistance where Cooper pairs are important. Okay, so this is a blockade of the current by Cooper pair. And the maximum is when you start to depair electrons and depair Cooper pairs now by the magnetic field, and critical field is here somewhere 3 Tesla or so, and then you go back to metallic behavior. So that is one of the indications that really the superconductivity is responsible for the insulating behavior, as counterintuitive it sounds. It is not a band insulator. It's not a simple, it's a correlated insulator. Okay, and so also in titanium nitride, we find this stability that you can find this is swept from left to right, jumps in the potential conductance as a function of voltage, and the switching up here is at a different voltage than the switching down. It's hysteretic. And this is IV characteristics for different magnetic fields, where one sees this divergent shape. And Valery Vinocourt, he looked at these curves and says, this looks like Kosterlitz-Towers, but in this case, charge Kosterlitz-Towers, which is the dual of the vortex Kosterlitz-Towers. So also in Fischer, you can find such remarks that if the interaction between charges is logarithmic, you should get self-duality, because also the interaction between vortices is logarithmic. And then the model is totally self-dual, and then you should have a charge counterpart of the vortex Kosterlitz-Towers physics. Meaning you start, say, I prefer to think in terms of, say, superconducting puddles, which are all charge neutral. If you have a Cooper pair now jumping from one puddle to the other, you generate a charge-anti-charge pair, because one puddle has an excess electrons, the other has a missing, not electron, has an excess Cooper pair, and the other has a missing Cooper pair. These attract each other, and if the attraction is logarithmic, you should get Kosterlitz-Towers physics. So this was the interpretation of Vinocourt, which got heavily disputed, to say the least. So the dispute was coming then from the Weizmann side, and also by famous theoreticians here, who said, well, you should not measure differential conductance, because then you don't have sensitivity. You should really measure the DC current. And if you measure the DC current, you find that there is current flow also below the jump. And on this logarithmic plot here, one sees the jumps are there. And they, together with these theoreticians, explained these jumps in a very simple way, namely as a heating instability. If the resistance is strongly temperature dependent, then a little bit of heating produces a strong decay in the resistance, and at finite bias voltage, much more current, much more heating, and therefore a thermal runaway. So that is the physics behind this heat balance equation. Here's the power that you put in. If the resistance here in the denominator is strongly dependent on the electron temperature, then the electron phonon coupling resistance that you have here, how the electrons get rid of their power to the phonon bar, is too weak, and get this runaway. So basically, they say if you assume IV is intrinsically linear, you get coupling, and then you get such jumps. So these jumps are not related to spectacular physics, but just to what simple insulators also would do, which is an argument one cannot immediately contradict. It is a possibility. And well, but that was not the whole story. So Vinocourt termed this the super insulator in the spirit of the duality of Fischer. Yeah, was not accepted. But still, people agreed that the insulating behavior is actually coming from superconductivity. And an important experiment here by Benjamin Sassepé was to do tunneling spectroscopy of strongly disordered indium arsenide films, where actually at some places you find spectra that you would expect that look BCS-like. At other places you see that there is not much of the coherence peak that you would expect. So this is here again differential conductance as a function of voltage, impossible to read, I'm sorry. But this is what you expect from a proper superconductor. This is not so a proper superconductor because these peaks are missing. So the statement in the end is, if the peaks are missing, this means electrons are incoherent. They are still paired, but they are localized and cannot contribute to the supercurrent. And here actually they count basically how much area they have without coherence peaks versus what is the resistance. And so orange here is the areas where you have coherence peaks. Here you should have the supercurrent. And if the temperature is higher, then you get all the peaks here, okay? And then you also get the resistance. So this is the picture of Feigerman and others, which basically say you have individual localized superpairs which are not able to sustain.
Christoph?
Yes.
This picture was proposed by Nandini and me 10 years before Feigerman. So I
yes.
really do object to that characterization of this work.
Yeah. I'm sorry. Your name still comes.
That's fine, but I'm just...
Yes, I learned something. It's the first time that I give this talk. Right, so... Yeah, but I think there may be differences in the detail, but it's not what I don't know how much time I have. 10 minutes? 20 minutes. Okay, so I think if you don't ask too many questions, I have a chance to get. But please ask, and it's not necessarily that I get to begin. Okay, so these are another examples of STM spectra, and here comes now Moit, who already 20 years ago has proposed that actually say in the presence of strong disorder, the Bourgeois-Dijen equations tell you that the magnitude of the superconducting pairing potential becomes spatial dependent, fractionalizes more and more, and into droplets. So this is all here from Mohit's paper, where there are areas where there is, so these are 3 different levels of disorder, and the horizontal rows are 3 different positions in space, basically, on these color maps. And you see here is always a proper gap. So this is the weakly disordered case. Here the gap is sometimes there, sometimes, it fluctuates in size. Here there are always coherence peaks. Here are sometimes coherence peaks. And here the gap is still there, but the BCS shape is gone. And you see the local pairing amplitude was calculated here. This is a relatively strong superconductor, pairing nearly everywhere, less pairing, and here only sparse pairing. Okay. And this is an experimental counterpart, a bit later than this first experiment here by Benjamin. This is also here from Paris, from Imaronichev, Strunk, who find that there is a topography. There is a density of states, and if they correlate the topography against the density of states, they see the spatial disorder of the surface has nothing to do with the distribution of all the parameters inside. That is, the autocorrelation shows that there are superconducting areas of a typical size of a few 10 nanometers. This is what the superconducting droplets are. Yes?
So these STM measurements on a strongly correlated or strongly disordered system, what could be the effect of the tip and its own screening on observing such a system?
Good question. I think all the experiments so far were not on the insulating side. They actually, okay, I should have prepared the scales, but you see here in the Benjamin's experiment, the scale here goes from 240 to 280 microwatt, which means your gap fluctuates a bit. But it's still strong. And this was the most disordered film that they had. Now, this is theory, then you can go everywhere. But the problem is if you come with your tip to an insulating film, then quickly your film resistance is larger than your tunneling resistance. Yes. This is not what you want to have in STM.
So I have to say that we have done it into the insulator, not with an STM, but with a tunnel junction.
I'll show in a second. Okay, so this is the local picture. Then also in Regensburg, there are some people that now bring, say, full cell consistency in this scheme and do not change the picture. And now comes other evidence for pairing on the insulating side. First experiment is here coming from Danny Shahar, who took a film, drilled some holes inside, 40 nanometers, and then measured films in different oxygen states. So this is a superconducting film. You see here 10 kilovolt, and it gets nearly superconducting. And that is a film in the insulating state, but the same oscillations. So these are little Parkes oscillations. It's a consequence of fluxoid quantization. It's a classic experiment from the 60s that demonstrated that there's 2e Cooper per charge, for instance, and that you can do this in an insulator is slightly disturbing. Because it tells you that there is a path around this hole through which the superconducting phase is not interrupted. Then is the experiment that Aviat was referring to, the superconducting film and insulating film, and then tunnel measurements on this. And you see the insulating film is far from being PCS, but it has some coherence peaks. The superconducting film has much less coherence peaks because these are extended junctions. They average over a large area.
It's the opposite.
Opposite?
Superconductors has more coherence peaks.
I understood that red is the insulator.
Yes.
So this has less peaks than the blue thing. Huh?
Same color, so that's whatever.
So the insulator has less coherence.
That's what I wanted to say. Sorry if I mixed up the words. Yes. Thanks. And you can do this also with, say, combined tunneling and microwave spectroscopy, where you see a clear gap in the insulating state, and then say little response here on the microwave side, but the tunneling still shows this gap. So what I want to say in the end is there's lots of evidence, microscopic, local, and macroscopic, that the insulating state holds Cooper pairs. And it's an insulator first understood, and I think so far we don't understand much.
I think in this last experiment, the difference between tunneling and TRS, you tell me if I'm wrong, but is that on the tunneling side you have a counter electron which modifies the coding. Oh.
Yeah. So that's the reason why these curves here are flat. Sorry, this I put in only this morning. I was a bit tired. And then maybe I missed the detail here. So, yeah. But what I want to say is there are multiple probes that point into the direction that this is a superconducting insulator. And now I have less and less time, but say now motivated by the pictures of emergent homogeneity, our point of view was, why don't we try to model now this insulating superconductor as a random network of Josephson junctions? Because if we can do that, then we can learn what is known about Josephson junction arrays. And there they tell you, well, there should be unbinding of charge-anti-charge pairs. In other words, there is because of the Soulis transition of charges. If these arrays are in the insulating regime, meaning that the Coulomb energy is larger than the Josephson coupling. So basically, the origin of the insulating state is the Coulomb blockade of Cooper pairs in these arrays. And there are some examples here where even the resistance can become stronger than activated. They call it a precursor of charge positive Soulis transition in the tunneling array. this point of view is not universally accepted, but meanwhile there are now two experiments. One from Weizmann, evidence for a finite temperature insulator. Meaning an insulator where the resistance drops to zero at a finite temperature. I mean, first they have killed the super insulator, now they have a finite temperature insulator. And the temperature dependence here is red is in the deep insulating regime where it is Ebroslovsky. Blue here really goes down at a finite temperature, that is some 40 millikelvin. Sorry. But there's a very clear difference between more conventional insulation at high field, 12 Tesla, and exotic insulation at low field. These are the activation curves where it has this upturn here, which is stronger than activated, like it is seen here also in the arrays. And then at high field, it kinks in the different direction. So this is now, again, the experiment from Tatiana again on niobium nitride. Formula differs only in the square root here, and the square root comes from the charge Poiseuille's Taurus. So this is just the charge counterpart of what we have shown you on the voltage side before. So probably DC transport experiments will never tell what is the nature of this insulator. We should find the new observables. So the question, what is the mechanism of destruction of superconductivity, is, say, what I have summarized still open. Do we have these Josephson-coupled droplets, or we have something much more fractionalized, multifractional or so? That is where the main disagreement is. What is the role of Coulomb interactions within the bosonic approach? I think it's not clear. What is the transport mechanism of preformed Cooper pairs? It's also not so clear. Sometimes it is Ebroslovsky, sometimes different laws. And when eventually hopping of Cooper pairs transitions to hopping of single electrons, when we have really destroyed all superconductivity. So this should all be somewhere, but it is in the quite a lot. So now, if I still have okay, yes. Questions so far? I need 5 minutes for the remaining slides. Yes.
You stated that the maximum in the in the RFB curves can be explained by a point where the pairs are not important anymore. Basically, the electrons take over.
And they get gradually destroyed. Yes.
How can it be explained that these maxima shift towards higher magnetic fields with increasing temperature?
Yeah, I think effects are not so strong. So here you would say they reside at the same place. Okay? I mean, we can look through the data, but I think this is not a strong effect. You need a.
I beg to differ, actually.
What?
I think, at least in my samples, you see a change in something like 1 Tesla.
But your samples are much deeper on the insulating side than this.
Yeah, that is true.
So I would not necessarily compare them.
Oh, yeah.
Question?
Yeah. No, I didn't get the picture from the right plot. So you buy a magnetic filter.
Yeah.
And so when the resistance goes down is where Cooper pairs are destroyed.
Yeah. Then we get back to metallic behavior.
It's not really metallic looking for resistance. So it's much more complicated than that.
Yeah. So this is per sheet. This is 100 kilo ohm. Yes. So this decay is gradual and also strongly depends on temperature. I mean, there is a.
Do you have any understanding about that state? I think it's not. That state is not.
No, actually. So this is in this year we had 2 PRLs. This is the one for the insulated behavior. There's a preceding one, which is called quantum metallicity in the high field limit, where we have analyzed these types of decays here. This is the typical Tatiana view on extracting some pattern on a limited amount of data. So it is worth to go back and see what is really going on there, whether this is really quantum metallicity or not.
think it is also some kind of exotic state.
Yes, but
it hasn't been studied enough. Really.
But the temperature dependence is weak.
Right. But the resistance is high.
What I compared.
Well, you have 100 kilo ohms and you have a very small, very weak temperature. I don't see those things there.
Yeah, I agree. I agree that it is exotic, but I would restrict the word insulating for the giga and teraohms. So this is my personal taste. It's not universal. Yes?
You mentioned several times that charge unbinding causes less thermals.
Yes.
Could you say a few words about why you would expect a logarithmic interaction between charges?
Yes. So this logarithmic interaction is actually Coulomb interaction in 2 dimensions.
Yeah, but the field lines are not confined to the plane.
Let me explain.
Yeah.
So in these Josephson junction arrays, the electric field resides between the plates of the tunnel junctions. And that is why in this case it is 2-dimensional. The field does not go into 3-dimensional space, but remains in the plates and in the plane. And then you get this logarithmic interaction, which was happily accepted here. You see, this is 1990. People in the end said, okay, probably don't quite reach there because there is an electrostatic screening length, which is the counterpart of the curl penetration length. And this electrostatic screening length can be calculated for such arrays, and it's rarely longer than 10 lattice spaces. So there one is in the opposite regime, where always your screening length is shorter than the extended length. Now the claim of Tatiana, you see, this is the square root plus formula that she extracts here, yeah, so it scales quite beautifully. This can be explained if the dielectric constant, macroscopic dielectric constant of that film is super large. Because also then field lines that emerge from localized charges do not go into 3-dimensional space, but they want to go into the high epsilon material, which is your thin film. And then again, you get a 2-dimensional logarithmic Coulomb interaction.
Is that true here?
That is a very good question. Of course, the Hostile guys said, no, this is never possible. This cannot be. But we have a poster outside where we measure an epsilon of 60,000.
60,000.
And this is still relatively far from the transition. So for the Tatiana scenario, you need a few 100,000, which sounds unphysical, of course. But as I said, we now started to measure epsilon in this insulating regime, and it is large. I'm not married to any theory or model. I just want to understand what is this insulator.
I want to say that I think 100,000 is possible.
Sure. After that, I think so, but we have to verify. Okay. So that is the charge. Yes, please.
When you measure the IV curves, when you measure the current voltage properties of the film, so let's say that there is a superconducting fraction inside.
Yes.
And because of the finite voltage, it would imply, based on the work of Josephson and Aslama-Zablarki, that the order parameter would also be dynamically fluctuating in time. So is it possible that we have, and which also means there is radiation emission?
If we have
different characteristics of radiation emission on 2 sides of the superconductor insulator transition.
Well, we would be happy if you have emission at all. I mean, in this island picture, of course, you can have a voltage only if there is a dynamics of the phase.
Yes.
I fully agree. And this tightly quantum synchronization was actually motivated by that time dependence. Yeah, so this is quite far beyond our experimental access so far. Yeah. One would like, with a little antenna, to see whether there's some Josephson radiation emitted. It's for the new generation of experimentalists, it's a proper challenge. More questions? Yes?
Array response. I think you showed earlier. And the thought on the slide earlier. But Yeah, I think a couple of maybe it's comment on why the prefactor for all of the curves fits to h1 squared roughly.
No, I cannot explain that. It is an observation. I don't find them now at the moment. Here.
Yeah.
And then,
I guess in your samples, if you go to even lower temperatures, do you see a saturation in your resistance?
no.
It continues straight line to the lowest temperatures.
Depends on which temperature you get on.
No, that is, you see, this is your 10 mega ohm. This is also relatively low because at that time you were not equipped for these extremely high resistances. But if you have an extended film, then simply your resistance grows beyond the detection if the temperature is low enough. So, but that means you really have to be at below 50 millikelvin, then you can get arbitrarily high, no saturation. That is really interesting about this class of materials as opposed to the next one, which I'll discuss in a moment.
Here it stops at 50 mils.
Yes, so I mean that depends on a number of parameters that we see. The talk would be overburdened if but here you can see this goes already up to giga ohms.
Sure, that's
10 to the 9. And here, where is it? This is sigma. Sigma goes to 10 to the minus 12 teraohms. And even for the F-Moshlovsky, it is 8%. Yeah.
I'm not sure it's a resistance that's limiting. It may be the temperature.
But you see, it's not limited. It grows. The question was whether it saturates at some point. And you see on these things, there is no saturation. This is inverse here, F-Moshlovsky way of plotting. This is the lowest temperature, and there is no saturation of the F-Moshlovsky.
But this, have they not just cut it off? Yeah, sure.
I mean, there is a detection limit, but I find the teraohm already slightly impressive. Yeah. You want more? Yeah, then you have to do many squares in parallel. So Max has 1,000 squares in parallel. Then you can go to higher resistance. But compared to all the situations at the kilo ohm level, this is infinite.
Yeah. I just asked because so you mentioned the kind of heating explanation of the jumps.
And these experiments are done super careful, both of them, right? So that on this, you cannot measure with a log-in or so ever. You always have to measure a full IV characteristic and restrict yourself to the linear regime. Like in the vortex case, in the Costa-Vestalis, when you show an R of T curve, each point is a full IV characteristic because in particular close transition, it becomes immediately nonlinear. And you really have to be super careful in order to get linear response. Okay, 5 minutes? Yeah. So now I promise to show normal metals in 2 dimensions. So this guy is Sergei Kravchenko, I think from Boston, published here this paper 1996, saying that there is a metal insulator transition in a MOSFET, high mobility MOSFET, at densities which are here 10 to the 10, 2-3 orders of magnitude lower than usually in 3-dimensional electron systems. And they see something like this. The guy nearly got kicked out from his university because he said there is something impossible. And but the effect refused to go away. And eventually, so this is for Moit. So this paper here, 2001, is a review article in Reviews of Modern Physics with the very same Elihu Abrahams, who was author of the No Metals in 2 Directions, in 2 Dimensions. So this is now metals in 2 dimensions. So if you switch the polarity of your statement, that allows you to continue with high impact applications.
Wait. Yeah, it was not fraction.
Huh?
Yes.
Only to strong interactive systems.
Yes. But so this caveat that scaling theory works only in absence of interactions was graciously omitted and didn't avoid the difficulties that the poor guy had, right? because he was contradicting the non-interacting theory, which became so strong that the sociology was comparatively strong. Sociology and science is something else. Okay, so this is just a teaser. So this is again many experiments are said, but in the end, the physics behind these observations is present, not understood, which tells you interaction plus Coulomb is really tough.
But that's 2001. Has something happened in the 25 years after?
I admit I don't know. Not that I heard of.
Okay, thank you.
So let's. These are here now connections also on old paper. You see, nearly from the also quench condensed films, but films that actually produce granules. So if you wish, these are random Josephson junction arrays, and they all show, you see, both here in the superconducting regime there is a saturation, in the insulating regime there is a saturation. Here also, there also. So that is low temperature saturation observed. Then you find this in arrays of SNS junctions. So this is 2012. Here, finding a forbidden state of matter. A metal in 2 dimensions was still good enough for nature physics in 2012, and also in 2014, where this is a similar array. Tin droplets on graphene, which are also produced Josephson coupling. So this is something that is relatively ubiquitous. And then came this shot from the side that we had yesterday already, that in TMDCs, eventually semiconductor physicists have discovered superconductivity and had to learn filter. And if they filter, then these things go away. But I think this is not the whole explanation, and this is now my homage to Claire. This is an experiment of Claire, which also shows that here, both on the superconducting side and on the insulating side, there are these resistance saturations. And in this case, we got a sample from Claire, this one here, which is 60 millikelvin TC. And we had a hard time in actually getting superconducting at all in our laboratory. I thought we understand filtering and so on, but we really had to work to get this film superconducting. So in this sense, I think this is one example where the result is solid and this saturation really does exist. Thank you so much for your patience.
Yeah. So then,
yeah, I have a remark about theorems in physics and a statement like this. I think they should always be taken with a grain of salt. And that, I mean, I remember about the fact that there are no crystals in 2 dimensions because of the Mermin-Wagner theorem. And now we have graphene, suspended graphene, plenty of 2D samples. I mean, there are always assumptions in the theorem that can be.
Yeah, so this is the difference between math and physics. In math, the theorems are always correct because you're free in your definitions. In physics, you have to start somewhere and try something, and then you make a statement, and then nature comes and shoots something from the side, which validates the conditions. Like equipartition theorem, right, is another famous theorem which is wrong, which in math would never be called theorem then, but it led to quantum mechanics and other things. It is simply the way. We just should be maybe a bit more cautious with the sociology.
So actually, I would also like to, as a theorist, I would like to make a comment. Theorems in physics are also very important, yes. But we have to understand what the assumptions are. Because if we find a phenomena in the lab which violates the theorem, then it allows us to see how we have evaded the theorem. So I think to just say that the gang of 4 was, okay, people took it too seriously, but they said right up front, in the absence of interactions, this is what would happen. If you see something different, that means interactions are playing a very important role.
I didn't mean to insult theorists. I agree fully with you that if something is wrong, it is interesting.
Yes.
because it means we didn't understand everything.
Maybe this. There. Okay.
Yes.
No, you have the question.
Just a question. I mean, localization in metals, we know there are different behaviors, for example, in the spiral systems or on a surface of topological insulators where you have a single Dirac cone. There are special kinds of systems that have different localization properties. And then what about in superconductors? Are you aware of any kind of system like that? Maybe you have additional symmetry type of system that would change, that would be completely outside this.
I mean, there is nothing immediate. I would say so far the investigation of these topologically non-trivial systems and so was all well in the metallic regime. Now there are also topological properties, say, of disordered systems. So this is a field that starts to emerge, and topology is active also there. I cannot say much to this, sorry.
Yes,
there's a very early prediction following Abrahams et al. That if you have a non-interacting system, but with strong spin-orbit coupling, then you would get actually a metal insulator transition even in 2 dimensions. The sign of the beta function flips. I was wondering if there's any experimental evidence for a metal insulator transition for non-interacting art.
That's a question to you.
In the presence of strong spin-orbit coupling?
I thought that you study indium antimonide, and that has a very strong spin orbit.
Yeah. But yeah, no, I know.
Not a different ensemble.
Okay. So, anti-localization has been measured.
That's true, but I was asking about that has certainly.
There would be strong anti-localization.
The metal insulator transition with disorder in that system.
There's
prediction,
right? But you're asking about the.
Yes.
That has.
So usually say in the superconductors in the old way, spin orbit interaction just randomizes your electron spin, meaning that you evade the Pauli limit. So this is this Elliott-Jaffet type of spin orbit interaction where each impurity rotates the spin by some degree. This is not what you need for these beautiful topological states. There you need a precise texture, not some random thing.
Maybe this is a good moment to stop and